welcome to the deep dive. Today, we're looking at a paper that really throws a gauntlet down. It challenges, well, maybe the last 5 years of AI development.
Yeah, it kind of tells the whole industry, hey, if you've just been chasing speed and parallelism, you might have missed something pretty fundamental for building smart agents.
We are diving into recurrence-complete frame-based action models.
And it's more than just a new architecture, right? It's a theoretical stake in the ground. The core idea is that this bedrock assumption of modern large models, that massive constant depth parallelism solves everything, it just doesn't hold up for these long horizon stateful agent tasks.
Okay, so for the folks listening, maybe engineers, researchers trying to keep up, let's hit the main points fast, like the 60-second version of why this matters.
Right, so point one. The theoretical impossibility, they argue pretty convincingly, I think, that if your architecture lets you fully parallelize the forward or backward paths thing, constant layer, transformers, Mamba, S4, that kind of thing, it cannot be what they call recurrence complete. It just doesn't have the needed serial depth.
Which then leads to practical problems for agents, right?
Exactly. That's point two. Input aggregation criticality. For tasks where an agent absolutely has to keep track of state step by step, serially, these parallel models essentially break down. Once the sequence gets too long for their fixed, shallow, sequential capacity, they basically, lose track of the latent state. Long-term memory fails.
Okay, impossibility, practical failure. And point three is their proposed fix and maybe the surprising payoff.
Yeah, the solution and the scaling. They introduced this recurrence-complete frame-based action model. It's a hybrid, a transformer head for perception, bolted onto a deep LSTM temporal backbone. And the payoff they show is kind of wild. Training loss follows this strict power law with sequence length, so even though longer sequences take way longer per step.
Like linearly longer wall time, right? Which sounds painful.
Totally painful. But counterintuitively, those longer runs end up being more efficient overall. They hit better loss faster versus wall time compared to shorter runs. The takeaway is serial computation isn't just necessary, it's ultimately what scales best for these tasks.
Wow, okay. That definitely sets the stage. Let's dig into section one then, the theory. Because this whole idea of true depth seems central. How are they defining that differently?
So true depth isn't just layer count. It's the length of the longest chain of operations in the model's computation graph that must happen sequentially, one after the other, separated by nonlinearities. You absolutely cannot parallelize these steps.
Right, and that's the key difference. A standard, say, 12-layer transformer, whether you feed it 100 tokens or 100,000, its true depth is constant, right? Order one.
Exactly. The final computation for token 10 doesn't strictly depend on the final computation for T1 having finished first in a serial chain. But think about a classic RNN or LSTM. The hidden state EDRs is literally computed using a 2-doll.
Okay.
That forces a dependency chain. Its length grows with the sequence length, 2 docs. So their true depth is omega.
So we've got this fundamental split.
Yeah.
Constant OBR depth versus sequence length dependent omega nub.
Yeah.
And this leads to their concept of recurrence completeness, or RC. That's the goalpost they're setting up.
Yeah, RC is the big one. A model is recurrence complete if it can, in theory, represent any recurrent update, like notadia, GHT1, XT, where tilers can be basically any function, crucially including non-associative functions.
Non-associative. Why is that the key part?
Because if tilers were associative, you could use clever tricks like parallel prefix scans, that's kind of the magic behind Mamba and other state space models, to compute the whole sequence in parallel, or at least much faster. But for a general non-associative update, there's no mathematical shortcut. You just have to compute it step by step, serially.
Ah, okay. And that's where the impossibility results come.
Yeah.
This is the core theoretical argument.
Precisely. They prove, and the proofs are in the appendices for those who want the details. Theorem 1 and Lemma 1 show that if your architecture allows a fully parallel forward or backward pass, it mathematically cannot be RC.
Okay.
And Theorem 2 goes further. Even if you use those parallel input aggregation tricks, like the prefix scans in Mamba or S4, you also give up recurrence completeness.
So the choice for speed, for parallelism, comes at a fundamental cost. You literally build a model that cannot represent certain kinds of long-term, non-associative dependencies. It's not just about maybe needing more parameters, it's a hard limit.
It's a hard representational ceiling, exactly.
Yeah.
You trade away the ability to handle these worst-case serial problems in exchange for faster training and inference.
Okay, that's the theory. Now let's connect that to section 2, how this limitation actually makes agents fail in practice. You mentioned input aggregation criticality.
Right, but first we need this idea of input length proportionality. It's just a way to describe tasks where doing the right thing at time step requires correctly processing information across essentially all $2 previous steps in a strictly serial way. No shortcuts.
Like their synthetic task, the FRJT, the forward referencing jumps task.
Yeah, that's a great example. It forces the model to follow these jumps in a sequence, where the destination of the jump depends on the value computed at the current step. It's like pointer chasing. You can't know where to look next until you finish the current step. Data-dependent control flow.
If step 2 tells you what data you even need for step 2 plus 1, you just have to wait. That's serial dependency by definition.
Exactly. And input aggregation criticality, or IAC, is what happens when a model that is not RST tries to do one of these input length proportional tasks. There's a critical sequence length, not off, beyond which the model just falls apart.
Why? What's happening internally?
Because the task itself demands, say, not sequential operations, but the non-RC model, with its constant true depth, can only perform a fixed number of truly sequential operations, maybe proportional to its layer count, LLANA. When NA gets much bigger than NALR, the model just doesn't have the sequential bandwidth. Its internal representation of the state degrades, it loses track.
And this seems especially bad for the kinds of agents people are trying to build now, like coding agents or ones that use tools. Why are they so vulnerable?
Because those agents are constantly dealing with partial observations and actions that have side effects on a hidden state. Think about a coding agent seeing a stream of Git diffs. The actual state of the code file, say to style, has to be computed serially. State is some side effect of applying delta to same dollar.
Right, the file system state or the terminal state, it changes based on every single previous action.
Exactly. The environment state itself evolves serially. If your model can't accurately track that latent state, say basal, over thousands of steps because of IAC, it's eventually going to make a mistake. It'll issue the wrong command based on an incorrect understanding of the world.
So even if a big transformer can see the whole history in its context window, it doesn't have the internal machinery, the serial machinery, to correctly aggregate that history into an accurate, persistent belief about the current state.
That's the argument. It can read the notes, but it can't keep the running tally correctly if the tally requires too many sequential steps.
Which brings us to section 3, the empirical tests. And these results, honestly, they kind of go against everything we've been optimizing for. Let's talk about that FRJT task, again, forcing serial jumps. They put time parallel models up against a simple single-layer LSTM. What happened?
Yeah, this is where it gets really stark. As they increase the task difficulty, the maximum number of serial jumps required, D-low dollars, the big parallel models like a 16-layer Mamba or Transformer just hit a wall. Their accuracy plummeted. They call it an accuracy cliff.
Okay.
So for instance, at a maximum depth of 16 jumps, the 16-layer Mamba, which is a sophisticated model designed for long contexts, only scored about 0.879 accuracy.
Wait, hold on. You're telling me a single-layer LSTM, something we often think of as like hold tech, it did better?
Much better. The one-layer LSTM scored 0.946 accuracy at depth 16. It generalized significantly farther.
Wow.
It's about the structural match. The LSTM, with its inherent omega shrew depth, has a computational structure that naturally mirrors the task's theta serial requirement. The Mamba, despite having many more parameters, still only has constant Obertrue depth. It just fundamentally can't represent the long chain of state updates needed for the harder versions of the task.
That's a really critical finding. It's not just about capacity. It's about the right kind of computational depth.
And the second task they used, the Withheld maze position tracking, drives this home. The agent has to track its position in a maze, but 20% of the time it doesn't get told the outcome of its move. It has to infer its position based on the history,
forcing it to maintain a latent state.
Exactly. And again, the one-layer LSTM, almost perfect accuracy, like 99%, even when the required tracking depth gets really high, like 64 steps with withheld info.
And the transformer, what did it need to do to keep up?
The transformer could only maintain high accuracy if its number of layers, dollars, was increased roughly in proportion to the tracking depth. No dollars. To handle depth 64, it needed way more layers than to handle depth 16.
So it confirms the input aggregation criticality idea. To overcome the constant depth limitation, the non-RC model has to compensate by brute forcing layers, essentially trying to simulate serial depth with parallel layers.
Precisely. It shows that for non-RC models, you need depth proportional to the sequence length requirement of the task. Otherwise, performance collapses.
Okay, so the theory holds up. The limitations are empirically demonstrated. Now, section 4, their proposed solution, the Recurrence-Complete frame-based action model.
It's a hybrid, right? How does it work?
Yeah, it's designed to get the best of both worlds, kinda. Use parallelism where it makes sense processing the input within a single time step, a single frame, but enforce strict serial computation between time steps. And the input format is key here, these frames.
Right. They assume the input at each time step is a complete, fixed-size 2D view of the interface. Think of a terminal screen grid along with the next low-level action that the agent is about to take.
So you have a frame head, what is a transformer, doing the spatial processing within the frame.
Yep.
And then a main sequence model, the LSTM backbone, handling the temporal sequence.
Exactly. The frame head looks at the current frame, maybe an 80 by 25 terminal grid. It uses standard transformer attention, pooling, all that, to embed the spatial information within that single frame. But here's a neat trick. It uses what they call a terminating LSTM cell internally.
Wait, an LSTM inside the transformer head? Doesn't that defeat the purpose of using a transformer for the parallel frame processing?
Not really, because it operates locally within the frame. See, the content within the frame lines of code, text on the screen, that's also a sequence, right? But it's a spatially bounded sequence, and its length can vary. So this terminating LSTM runs sequentially over the tokens within that single frame, like the characters or words on screen, and boils them down into a single fixed-size vector representing the entire frame's content, let's call it $50. It handles the variable length sequential nature inside the frame to produce a consistent output.
I see. So it serially digests the frame's internal sequence to get one fixed-size perception vector for that time step.
Exactly. And that fixed-size vector 50L is what gets fed into the main temporal backbone.
Which is
a stack of residual LSTM layers, maybe with some MLPs in between. This part is deliberately, unashamedly serial and non-parallelizable. It embraces the sequential flow of time using the LSTM structure, including its constant error carousel, to hopefully maintain state accurately over very long durations.
Makes sense. Now, to train something like this, especially on long sequences, you need tons of data that looks like actual agent interactions. They built the data engine using GitHub, right?
Yeah, it's pretty clever. They essentially replay Git history. They take diffs between commits and reconstruct a plausible sequence of text editor states and the low-level actions, like keystrokes, that could have produced those changes. This generates paired data of terminal screen frame and next action.
And they needed a special format for this data.
Right, because they need long sequences. So they developed a highly compressed format called term stream X's. They claim up to 300x compression, which is huge. It makes these massive data sets manageable and streamable during training, kind of like decoding a video stream efficiently.
In training itself, they use full backpropagation through time. BPTT, which normally eats GPU memory like crazy for long sequences. How did they get around that?
They use a streaming approach with recomputation. Basically, they don't keep all the intermediate activations for the entire sequence in GPU memory. They compute the forward pass, maybe stream the LSTM hidden states out to CPU RAM, and then during the backward pass, they recompute the activations for the frame head on the fly as needed.
Gradient checkpointing, essentially, but tailored for this streaming setup.
Pretty much. The upshot is that their GPU memory usage becomes constant. Oh wait, $, with respect to sequence length. The trade-off is computational cost, it takes longer. But it means they aren't limited by memory for how long a sequence they can train on.
Which perfectly sets up section 5, the scaling laws. This is where that painful wall time cost starts to look like a good investment. This power law finding is the core empirical result, right?
Absolutely. They took their model, fixed the number of parameters, and just varied the sequence length, the LAR they trained it on. What they found was a remarkably clean power law relationship. The training loss at a given number of steps goes down like Lawler's raised to the power of alpha. So text loss approximate alpha.
And they measured that exponent alpha.
Yeah, on their Git-derived dataset, they found alpha was around a 0.318 after about 4,000 training steps.
Okay, translate that alpha approx 0.318 wheat for an engineer. What's the practical gain?
It means every time you double the sequence length you train on, keeping everything else the same, you get a consistent, predictable drop in loss around 19 to 20% lower loss plateau. That's a really strong scaling signal. Double the context, get significantly better.
And importantly, they found this wasn't just helping predict the end of the sequence better, right? Like sometimes happens with longer context in language models.
Exactly. The improvement was uniform across all token positions early and late in the sequence. That suggests the model isn't just getting better at recent context, but its overall internal persistent state, its understanding built up over the whole sequence, is genuinely improving.
Okay, let's tackle the wall time paradox head on. Longer sequence means each training step takes longer. You mentioned 20 minutes per step for one old Suvenchi 4 docs. That sounds awful. But you said longer runs eventually win. How does that work?
It's this wall-time amortization argument, backed by a proof in their appendix. Even though each step is linearly more expensive for longer sequences, the rate at which the loss improves per step is so much better because of that alpha scaling that it overcomes the higher per step cost.
So it's like investing more upfront for faster long-term gains.
Kind of. There's a crossover point. If you plot loss versus total wall clock time, the run trained on the longer sequence will eventually dip below the run trained on the shorter sequence, and from that point on, it stays lower. It becomes more time efficient to have trained on the longer sequence despite the per step cost.
That's huge. It basically says if you care about the best final performance for a given compute budget, you should always train on the longest sequence your hardware setup can handle because it will eventually amortize its cost. Don't artificially limit sequence length for per step speed.
That seems to be the implication, yeah. It really pushes the serial scaling hypothesis that unlocking better agent capabilities might depend more on scaling the serial state tracking ability via sequence length than just scaling parallel parameters.
What about things like chain of thought prompting? Doesn't that help models track state by externalizing it into the context? Does this RC model still provide an advantage then?
They touch on this. They argue that while COP definitely helps by putting intermediate reasoning steps into the context window, the fundamental problem of input aggregation criticality still exists at the perception layer. Meaning, even if the model generates thoughts, it still needs to read the current state of the world, the frame, and integrate that new information with its internal understanding accumulated over time. If the backbone doing that integration isn't RC, it can still fail to correctly update its latent state based on long histories, even with Quoto present. The serial backbone is still needed for robust, long-term perception and state tracking.
Interesting point. And one last thing on the architecture. You mentioned the long wall time per step actually makes it good for decentralized training. That sounds backward.
It does, but think about it. The main recurrent backbone, the LSTM stack, is actually not that large in terms of parameters compared to giant transformers. The bottleneck is the serial computation time per step, not necessarily the model size or communication bandwidth.
Okay.
So if each step takes, say, 20 minutes, you only need to synchronize gradients between workers every 20 minutes. The ratio of computation time to communication time is very high. This makes it potentially well-suited for training across a distributed network of less tightly coupled machines, maybe even using spot instances or geographically diverse hardware without communication becoming the bottleneck.
Fascinating. Okay, so wrapping up this deep dive, the argument seems really coherent. A strong theoretical case against pure parallelism for certain tasks, empirical evidence showing the failure modes, and a proposed RC architecture that, while slow per step, shows compelling scaling laws with sequence length.
Yeah, the core message is that for these long-horizon agentic tasks, serial computation isn't just a nice-to-have, it's apparently a hard requirement. The parallel first paradigm seems to hit a fundamental wall here.
They do acknowledge the elephant in the room, though the current wall time cost is still a major hurdle for practical deployment at massive scale.
Oh, absolutely. They're upfront about that. But the scaling results suggest the direction is correct. They even speculate that reaching truly emergent, human-like planning might require pushing sequence lengths to 105.55 frames or beyond.
Which implies the real bottleneck right now isn't the model design or the theory, but building the infrastructure capable of handling that sheer volume of serial computation efficiently.
Exactly. And that leaves a provocative thought for you, the listener, especially if you're involved in designing or training large agentic systems. Are you optimizing primarily for the parallel efficiency and speed metrics that have dominated the last few years? Or are you considering whether your architecture possesses the fundamental serial computational competence needed for the long-term state tracking these tasks seem to demand? This paper strongly suggests those might be conflicting goals.